What's up? This is Group 4. We're going to talk about our DC motor system so far.
The dead zone is the nonlinear behavior of motors below some minimum threshold voltage. The plot on the left shows the steady-state angular velocity versus input voltage, where the red line depicts the dead zone limit upper bound at 0.05 volts. Anything below this and the motor will not spin. The plot on the right shows the angular velocity versus time at 0.02 volts, with motor sputtering visible at time less than 0.2 seconds. The saturation zone characterizes the maximum input voltage until which the motor will still perform, following the same linear manner. The plot on the right is a continuation of the steady-state angular velocity versus input voltage plot from the previous slide, where the purple line depicts the lower bound of the saturation zone limit at 7 volts. Anything past this and the steady-state angular velocity remains the same. And around the purple line you can see a discrete transition between the linear zone and the saturation zone.
Motor constant Km is the ratio between the angular velocity and input voltages of the motor. On this plot we see a dead zone, a linear zone, and a saturation zone. In the dead zone, there's no velocity response to the input voltage. In the linear zone, we see a linear response to the voltage. And in the saturation zone, we see no increase of angular velocity in response to voltage. Interestingly, there's a small transition zone between 0.05 volts and 1 volt, where the motor behaves extremely nonlinearly. Time constant Tm is the amount of time that the motor takes to reach steady state. Here we see, in each zone, the value is relatively constant. In the transition zone, it's approximately 0.1 seconds. In the linear zone, it's approximately 0.09 seconds, and in the saturation zone, it's significantly higher at 0.125 seconds. Although this is not perfect and the transition range is not expected by our model, this is a fairly linear model of the motor. Tabulated here are the computed averages of the time constants. As you can see, the transition zone has a time constant of 0.1, the linear zone has a time constant of 0.08, and the saturation zone has a time constant of 0.12 seconds. These differ moderately from each other, but are not inconsistent with the model that we have generated. Here we see the transition zone in far more detail. As you can see, it asymptotically approaches the constant value of 9 for Km and may be considered relatively constant after 0.5 volts. Before 0.5 volts, a linear approximation is inappropriate. In the linear zone of the motor, Km averages to 9.03. As we can see, there's very low variance, and the linear fit works very well in this region. In the saturation zone, Km rapidly decreases and has a slight upwards curve implying an asymptotic approximation of 0. This is exactly what we would expect, as the velocity of the motor stays constant and the input voltage is increasing.
This piecewise table shows the motor constant versus input voltage averages and equations from the previous slides. The transition zone, which is 0.05 to 1 volts, had an average motor constant of 6.997 revolutions per second volts and had the following equation. The linear zone from 2 to 7 volts had an average motor constant of 9.032 revolutions per volt seconds, and that had an equation of a constant 9.032. And finally, the saturation zone from 8 to 10 volts had an average motor constant value of 7.326 revolutions per volt seconds and had the following equation.
Still using the time domain technique, let's take a closer look into our data and compare it to theoretical values. The step response plot on the right shows that our angular velocity in the steady state region actually fluctuates a little bit. This can be explained by the EMF resistant force that acts on the brushes of the motor as it rotates, and even due to the fact that although we set our input voltage to 5 volts, it might fluctuate a little bit while we were acquiring the data. The team is actually impressed with how close the curve for the experimental and theoretical step responses are. This can be evidenced by the calculated 0.23% difference in Km and 11% in Tm. However, taking into consideration the assumption of no friction and no inductance, one would expect the blue or the theoretical curve to show faster angular acceleration and to achieve steady state earlier than the experimental one. What actually happened is that they both achieve steady state basically at the same time, and the experimental curve shows a faster acceleration for a small part of the time domain, from roughly 0.05 seconds to 0.4 seconds. This explains the high ATM for the theoretical model. Now let's add mass to the flywheel and see what happens to our values of Km and Tm. Since Km does not depend on the inertia of the flywheel, we expect it not to change due to changing mass. With an increase of only 0.3%, we can see that our expectations were met. On the other hand, Tm increases. But since Tm is a function of the inertia of the flywheel, we expect this to happen. It's also interesting to observe that, as expected due to the increase in the time constant, the curve of the flywheel without the mass shows faster acceleration and achieves steady state earlier when compared to the one representing the heavier flywheel.
So here we have the experimental and theoretical Bode diagram. We use the corner frequency from the gain plot of the experimental because it's in the phase lag of the experimental data. It goes much beyond negative 90 degrees, and that is because the motor in reality is a second order system. So it kind of shows here that the first order assumption of the system breaks down when it comes to phase lag. As far as the design problem goes, for case 1, the first order system would work very well because the step response holds very well, and 0.1 hertz has a very low phase lag. So we could roll with a first order assumption using K as 9.032 and T as 0.084. Case 2 would be a little bit different story because while the step response would still be accurate from the first order model, the phase lag would be much more significant than the first order model suggests. So we would need a second order model for that case. Frequency domain analysis is very good for transient responses, so like with different frequencies, whereas time domain is not as easy to get frequency response based on time series data. However, time series is very useful for getting steady state parameters like the omega steady state. It's nice for getting some transients for step response as well.